Morning, guys. Hope you guys are all doing well. This will be your second video that you're going to have to watch for this distance learning. I hope you guys are all doing well and you're staying healthy. If you're having any problems or questions, please reach out and let me know. I'd love to be able to help you out. All right. Well, let's get started here. The next chapter is chapter 17. Chapter 17 is about elements and their properties. Okay. We've talked about the periodic table a little bit before. There's 118 different elements. And of those 118 different elements, every single atom of all the bazillion atoms on our planet have to be one of those. And then obviously things are subcategorized a little bit more. We have metals, non-metals, and then we have a small group that are kind of in the middle. They're called metalloids. They are ones that have properties that are kind of both. We'll go into the details of that in a little bit here. Okay, 17.1 then is about metals. When we think of metals, oftentimes we think of, things like aluminum cans or iron or steel, that kind of stuff. Metals, just very generally, are elements that are shiny, malleable, and ductile, okay? Being malleable means that you can pound it into shape, and being ductile means that it can be pulled or drawn into wires. We'll talk about that in a little bit here. They tend to be good conductors of heat and electricity. And then also they're typically solid at room temperature. The only exception to this is mercury. Mercury is the only metal that's a liquid at room temperature. It doesn't turn solid until it reaches, I'm not even sure what temperature it reaches. Gallium is a solid at room temperature, but it has a really low melting temperature. So I actually have some gallium right here. We're looking at the picture there, but I have gallium, okay? And if I held this in my hand until this piece of gallium warmed up, it's pretty cold right now because it's at room temperature, but if I held this in my hand until it melted, or until it reached the same temperature as my hand, it would melt. And if I hold it next to my hand, the surface of it will melt a little bit. It's not quite as easy as what they're making it look in this picture to get it to melt, because it requires a little bit more temperature than that, or a little bit more heat than that. But it's kind of fun to play with. Once it's melted, it looks like mercury. It's really, really shiny. I have it in this little cup. This is actually a K-cup for my Keurig machine. And what I did was I put the gallium in a little beaker and then put that beaker into a larger beaker of really hot water. And it melted really easily and got liquidy, kind of like what we're looking at here. And then I poured it into the K-cup. If you look really close, you can see the detail that's written on the bottom of the K-cup there. I don't know if you can see that. So that's showing up on the gallium. Anyways, all right, here, let's keep going here. If something is malleable, that means that we can, hammer it, pound it into shape. It can be rolled into sheets. Oftentimes this gets used for jewelry, different types of foil. I mean, typically we're looking about aluminum foil, but there's different types of foil. We've talked about gold foil before, like Rutherford and his gold foil experiments. That's the picture that we're looking at down on the bottom left here. That's actually very, very thin sheets of gold foil. Can be used for electro wires and plumbing fixtures. Oftentimes, and because they can be pounded and molded, they get used for making coins and things like that. If something is ductile, that means that it can be pulled or drawn into wires. So basically what they do is they take a big chunk. It's like silly putty, right? I don't have any silly putty or even anything kind of like that. But imagine if I took a piece of silly putty or clay or something and I grabbed it and I started pulling on it, it would start to get thinner and thinner in the middle, right? I'm pulling. Imagine I just have imaginary silly putty there. If we can do that, then we say it's ductile. So it can be drawn into wires. And when we do that, then we can connect them together to make braided wire. So bonding in metals happens when we have those outer electrons that are given up and shared. So what happens is usually metals have anywhere from 1 to 3 electrons in their outer energy level. We talked about that in the previous chapter. And they tend to give those up relatively easily because they aren't held very tightly by the protons. So what happens then is those metals then, if they lose an electron, they become more, so think about this, they're losing an electron, that's a negative charge. So if they're losing an electron, they are becoming more positively charged, okay? Now, metals typically hold their valence electrons very loosely. So metallic bonding is a situation where we have atoms, or I'm sorry, not atoms, electrons that are able to be passed back and forth very, very easily. And that's really important for electricity to travel or be able, or electric flow or current to occur. Now, the gift that we're looking at on the bottom here, that's sodium is a metal. It's kind of shiny. If you look, if you can cut it, it's got a the surface of it. If you guys were here, I would actually, we could, well, hopefully you guys are here before the end of the school year. Maybe we can do that. But it's a very soft metal. You can cut it very easily with a butter knife, and it gets very shiny. But then the outside layer, it quickly oxidizes, and then it becomes sort of a dullish kind of a color. So sodium is giving up one of its electrons. It has 1 electron in its outer energy level right there. It's giving that up, and fluorine only needs 1 to satisfy the octet rule. So then fluorine gets that extra 1. Now those two become attracted to one another because of electrostatic interactions, meaning that opposites attract, right? Sodium becomes more positive because it lost an electron. Fluorine becomes more negative because it gained an electron, or it gained another negative charge. So in metallic bonding, because those electrons are held so loosely, those electrons are very easily passed back and forth, and it creates what we call a sea of electrons. Okay, those outer energy level electrons, they're very loosely held. They get passed back and forth very easily, and they're free to move around amongst all of the atoms. Okay, in the group of metals, okay, so when we look at the periodic table, typically we have non-metals over here in the upper right-hand side in this area, and then things to the left are what we call metals, and then right down the middle there's kind of a stair step, and we can't see it on this version of the periodic table, but that's what we call the metalloids, okay? Alkali metals are the very first group. You know, it consists of sodium, lithium, potassium, rubidium, calcium, and francium. And these are all reactive with water. Some of them, they'll react with water in the atmosphere. If we throw them in a bucket of water, some of them will spark and create hydrogen gas, and they can blow up, things like that. Sodium and potassium are definitely needed for nutrition. They help electrical signals to conduct throughout our bodies, or the bodies of animals, to help us sense the environment and maintain homeostasis, if you remember that. So they have 1 valence electron, right? Period 1 has 1 valence electron. You probably remember that from previous chapter. Group 2 has 2 valence electrons. We skip the metal, and we have group 3, 4, 5, 6, 7, and 8 valence electrons. So these group 1 elements, besides hydrogen, it's the exception, those group 1 elements want to create bonds with group 17 elements, because the group 17 elements have 7 valence electrons, okay? Well, in order to satisfy the octet rule, the group 1 elements have 1 valence electron. All they do is give up 1 electron, and then they're happy because their outer energy level is full with 8. They satisfy the octet rule. The group 17 elements, these are halogens. The halogens only need to gain 1 electron in order to satisfy the octet rule. So again, if we go back to the previous 2 slides ago, sodium is in group 1, fluorine is in group 17. Sodium wants to lose this 1 electron because then it has a full outer shell of 8 electrons, 2, 4, 6, 8. Becomes stable. It becomes an ion. Now it's more positively charged because it lost a negative charge. Fluorine has 2, 4, 6, 7 electrons. It wants to gain 1. And once it gets 1 from sodium, then fluorine is happy because it has 8. And then it becomes more negatively charged. Fluorine is negatively charged. Sodium then as an ion becomes positively charged, and they stick together then because of electrostatic interactions. Okay. Cesium is one of the group 1 elements. It's one of the alkali metals. It gets used in atomic clocks, as a matter of fact. Some of the isotopes are radioactive, and if they are radioactive elements, that just means that their nucleus will break down or give off particles every so often, depending on those elements have a half-life, and that's how long it takes for their nucleus to decay away. We'll get into details of that more in a different chapter. Microwave signals are given off by cesium, and this helps them to maintain a clock. I don't remember where this is, but this is, if I remember right, this is where the world's time is based off of this cesium clock, essentially. Now, the next group over in group 2, this is what we call the alkali earth metals, group 2 elements. They are also shiny, malleable, ductile. They have 2 electrons in their outer energy level. So guess, who are they going to want to pair with, or who are they going to want to create bonds with? They're going to create bonds with the group 16 elements, because the group 16 elements need only 2 electrons in order to satisfy the octet rule. And these in group 2 need to give up 2, right? So they very easily will form bonds with group 16 elements. Again, because the group 2, the alkali earth metals, are losing 2 electrons, they become more positively charged. The group 16 elements, if they're bonding with those, are going to gain 2 electrons, so they become more negatively charged. Again, then they stick together or they bond together because of those electrostatic interactions. Alkali earth metals burn in a lot of different colors. Oftentimes these are used in fireworks and things like that, because they'll burn different colors. Okay, and then we end up with a group right in the middle here. These are called the transition elements. It includes the lanthanide and actinide series down here in the bottom. They have a lot of different uses. We call them transition elements because how they behave and how many valence electrons they have sort of depends on their environment and what they happen to be bonding with. Okay, lots of different uses. Some of these are very, very strong metals like titanium. Some of them are used as alloys with iron, like making steel, or chromium is used to help protect materials that we don't want to rust easily. Some are alloyed to make jewelry, coins, currency. Mercury gets used for measuring temperature and pressure in different apparatus. But there are literally tons and tons of different applications for the transition elements, and those are just a few. We'll get into details of more of that stuff later on. Okay, we talked about the lanthanide and actinide series. This is what the periodic table would look like if the lanthanide and actinide series were included in the periodic table, not put down below. Okay, so the lanthanide and actinide series are down here. Most periodic tables, you're going to see them down on the bottom down there, because if you put them in, it pushes out the periodic table so long that it takes up more than a sheet of paper. And if it was all on one sheet of paper, all of the writing would have to be so small, it would be really difficult to see and read stuff. Okay, so they just take it out, they put it down below, and it works just fine to do it like that. The properties of transition elements, they tend to have higher boiling points and melting points than the main group elements. Okay, so main group elements are groups 1, 2, skip the transition, group 13, 14, 15, 16, 17, and 18. Those are what we call the main group elements. Okay. Yeah. Okay. So for example, tungsten, which gets, tungsten is used as, or has been used as a filament for incandescent light bulbs, because electricity can pass through the little filament and it can get really, really hot before it will melt. Okay. We probably heard Thomas Edison used tried 1,000 different things to try and make a light bulb work. Tungsten ended up being the thing that he wanted to use, or did use, because it can get really hot. I mean, you probably used everything from wood to iron to cobalt, or whatever. And what would happen is those metals would get hot as electricity passes through it, and they would melt, and they wouldn't be able to sustain light for very long. Tungsten, element symbol W, has a melting point of 6,000 degrees Fahrenheit. Okay, 6,000 degrees. That's really, really, really hot. Like, you know, if you had a really hot bonfire going, you're probably, I don't know, 800, maybe 1,000 degrees, but probably not even that high. Mercury has a melting point, and mercury again is the exception to all of this. Mercury has a melting point of negative 36 degrees Fahrenheit. So that's the temperature at which it would go from a liquid to a solid, or from a solid back to a liquid. Okay, so negative 36 Fahrenheit. So if you took a mercury thermometer outside and it was minus 40 actual air temperature, then you could probably get that your thermometer, your mercury thermometer, is not going to work. Now, mercury hasn't been used in, you know, regular thermometers or the thermometers that people would buy from the store in a very long time. They figured out a long time ago that mercury is toxic, it's carcinogenic, it causes cancer. And so they stopped using it in thermometers. And you can imagine like a high school laboratory or even a middle school laboratory that's using mercury thermometers, and how many of those thermometers would get broken, and the mercury would end up on the floor. And if you don't get it all cleaned up, it gives off fumes. And they found many, many years ago that a lot of old science teachers were starting to come down with cancer, and they figured out that that was probably a likely cause. Iron is one of the transition elements. It's essential for tons of stuff. We use it for to help create heme groups, or blood cells in humans. Oxygen molecules are held on to by those iron molecules. It's the main component of steel. We have like stainless steel is used for cooking instruments, or cooking equipment, or surgical instruments. Then oftentimes iron gets alloyed, meaning that it gets mixed with other stuff to give it some sort of properties that we might find desirable, like resistance to corroding. Manganese, you can alloy with manganese, and that makes it tough, so it doesn't wear quite as much. Nickel makes it tough, and if you alloy it with tungsten, it makes it heat resistant. Then we have what's called the iron triad: iron, cobalt, and nickel. These are right here in groups 8, 9, and 10. They have their atomic radii, meaning the distance from the nucleus to the outer part of the atom, is almost identical. And because of that, they have very similar properties, physical properties. All three of them, excuse me, all three of them are magnetic, or can be magnetized. And again, we use those for alloying with a lot of different iron alloys. The next one is the coinage metals: copper, silver, and gold. Kind of makes sense, right? Who wouldn't want a gold coin? I don't know. Again, they have similar properties because they're all in the same group. They're used for coins because they're malleable. They're relatively easy to pound into shape, or to turn into coins. And they're pretty unreactive. So like if we have a bar of gold that's been sitting on the shelf for 200 years, it essentially hasn't changed at all. Maybe it's gotten dusty a little bit, but the atoms themselves aren't breaking down because they're very, very stable. Silver and gold are relatively rare. Copper is not as rare, but because copper is being used for a lot of different things, especially like electrical applications, it's becoming more and more valuable. Chromium is in that group as well. Chroma is Greek for color. A lot of chromium compounds are really brightly colored, and they get alloyed with iron to make things corrosion resistant to corroding. There's a picture here of a car that was chromed out, the entire car. Chromium is also used for making jet engines because it helps to resist some really high heat. And it's also used in chrome plating things like rims of cars and things like that. Probably the accessories or parts of the body of a vehicle, those shiny parts are used in chrome plating. Zinc is the next one. Zinc is corrosion resistant, gets used for a lot of different processes. It's in the process of galvanizing things. And it's, I believe, zinc and copper. Yeah, zinc and copper makes brass. Probably watched that documentary. Actually, I don't think I showed it to you guys. You'll get to see it at some point, probably when you take chemistry, because I don't know if I'll see you guys before the end of the school year. But if you come back, we'll probably watch it. It's pretty fun. It's called Hunting the Elements. And then there's a lanthanide and actinide series. We call those the inner transition metals, okay? So if you remember right, those are the ones that are down here on the very bottom, okay? Lanthanide is the top one, and it starts here, or I'm sorry, everything's backwards. Lanthium is right here, and actinium is right there. So the lanthanide and actinide series are what we call the inner transition in metals. They're only found in Earth's crust. That's the only place we know of them. Some of those metals are used in nuclear power reactors, and they help to absorb neutrons of nuclear reactions. Some of the actinides are all radioactive. So the bottom row of those, okay, these are all radioactive. In fact, everything uranium and beyond, I believe, is radioactive. Or no, uranium is in the bottom row, so obviously uranium is radioactive. Some of the stuff above that is radioactive as well. Uranium is used for making plutonium, which is a nuclear fuel. Californium is one of those that's used for treating cancer. Here's californium right there. Uranium comes from a mineral called uranite. This is a picture of uranite mineral. Now, if you're hanging out with uranite, you're not worried so much about the nuclear reactivity causing problems for you like you would if it was like enriched for like a nuclear power reactor. That would be very dangerous. They're also I must have duplicated a slide here. Again, they're called intertransition metals, the lanthanide and actinide series. Some of the lanthanides are used for lighting applications. This is kind of a nice here because we have the periodic tables to look at. So the lanthanide series, and over here we have the actinide series. The lanthanides we also call the rare earth metals, okay? The actinides are all radioactive and they're rare and they don't exist in nature, okay? Everything beyond uranium does not exist in nature. So element number 92, so 93 and beyond does not exist in nature. The conditions on Earth are not right for those to exist. So those get created, and most of them probably in like a particle collider where they take two elements and they smash them together like we talked about in the previous chapter. Again, this is what the periodic table would look like if we had the lanthanide and actinide series plugged in. Again, it would make it look really wide and it would be difficult to see everything. So they make it smaller and put it on one sheet of paper. Metals are mined from Earth's crust. This is a gold mine that we're looking at. I think I pulled this from Gold Rush, Alaska, from one of the first 1 or 2 seasons, something like that. You know, this is a testament to how long ago I put this PowerPoint together. We're talking about the new elements that have been discovered, element 114 and 116. Well, now all of the elements have been discovered. We've got all the way up to 118. So we've made, in the realm of chemistry, we've discovered all of the elements or the atoms that there are in the universe. Okay, 17.2 is about the nonmetals. Again, on the left-hand side of the periodic table is where we have the metals. On the far right and upper part, we have the nonmetals, and then the ones in the middle here are what we call the metalloids. Okay, the nonmetals are usually gas, and if they are solid at room temperature, which most of them aren't, but if they are, they tend to be brittle and powdery. Okay, you know, probably like silt, or like maybe not quite as fine as dust, but pretty fine. They are bad conductors or poor conductors of heat and electricity, and those electrons are not free to move around like metals are. You know, recall the metals have what's called like a sea of electrons. When nonmetals are bonded to other nonmetals, they do what's called covalent bonding. So they're sharing electrons. When nonmetals bond with metals, then we call that ionic bonding. And those are different, and we'll get to those in a different chapter. Diatomic molecules are ones that have two atoms of the same element, and they are at a covalent bond, meaning that they are sharing an electron. Like hydrogen atoms typically don't want to go rolling around by themselves. They want to be attached to another hydrogen atom. Oxygen is the same way. They like to come in pairs because they like to bond to one another. And by doing so, it makes them a little bit more stable. So we call those diatomic molecules. Here's some more common ones: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You know, I'm not going to ask you about those on a test, but just recognize that they do exist as diatomic molecules. Okay, that brings us to the group 17 elements. These are the halogens. These are very reactive elements. In fact, fluorine is the most reactive element of all of them on the periodic table, and it also is a halogen. Chlorine and iodine are used in, the vapors, I should say, are used in different lighting applications or light bulbs. Fluorides get used or added to toothpaste, and there's fluoride in water. It can be used as a cleaning agent. There's a picture of someone that's getting their fluoride treatment. They don't do it like this anymore. Apparently, I was at the dentist a couple weeks ago, and they just have something they put on your teeth now. They don't have the little tray that you have to bite into, and they suck it out with the little sucker deal. Okay, chlorine and bromine are used for disinfecting pools and hot tubs, things like that. Iodine is used for disinfecting things for medical purposes. Individuals that have an iodine deficiency can end up with what's called a goiter. It causes inflammation in their thyroid gland. Over here, you can see someone is donating blood, and they cleaned off that area with iodine because it kills all sorts of bacteria. This is a plant called Sanguinaria canadensis. Its common name is bloodroot. And when you pull it out of the ground, if you can get underneath the roots and you can kind of pop it up, if you cut the root, it actually looks like blood. Now, this is kind of like iodine, and back in, I don't know how many years ago, they actually used the juice, if you will, from the roots to treat things like plantar's warts and things like that. They also probably would have used them for like painting and that kind of stuff. But this is what it looks like: Sanguinaria canadensis. And then finally, we have the noble gases. Those are on the far right-hand side. We call them the noble gases because all of the other elements want to be like them. They are noble, okay? Nobility. And that, back in the times, hundreds of years ago when they were developing, when they were studying all of this stuff, the nobles would be the people that we all wanted to be like, right? They have money, they have power, and so all of the elements want to be like the noble gases, okay? Oftentimes, some of those noble gases get used in things that are high energy or very reactive reactions because they're so stable that they won't even burn, okay? So they get used in like lasers. Argon, krypton, xenon, those are made in a laboratory, okay? There we go. Argon, krypton, and xenon. These three get used in a laboratory, or get made in a laboratory. Helium is kind of funny. It gets used in blimps and balloons and that kind of stuff. And one thing that's interesting about helium, or maybe worth mentioning, is that in 100 years, when all of the helium has been mined, because that's where it comes from in mines, when all of the helium that's been mined is all used up, scientists are going to be really angry that we use them to fill party balloons because they are fun and they float and they make your voice sound kind of squeaky and high. Also, some of these are used in, some of the noble gases are used in signs like neon lights and stuff like that. Okay, that's it for 17.2, the nonmetals, and now we have what's called the mixed group. That's 17.3. We call these the metalloids, okay? So the metalloids are right along this little stair-step line here. And those elements have properties that are both like metals and like non-metals, okay? So they, if you remember, the metals are good conductors of heat and electricity. The non-metals are very poor conductors of heat and electricity. The metalloids are, they're kind of in the middle, okay? So they kind of share properties of both. Boron is a metalloid that's used in laundry and heat-resistant glass. Gallium gets used in electronics or electronic components like the little like motherboards and circuit boards and things like that, because it allows a little bit of electricity to pass, but not very much. Also, aluminum, it's the most abundant metal in Earth's crust. Now, most abundant metal in Earth's crust, and it's strong, but very lightweight. So it gets used for a lot of different applications. Here's aluminum right here. Carbon is another one of those. It's in group 4. It's in one of the mixed groups. It's has 4 electrons in its outer energy level. It's the main element in coal, diamonds. Carbon dioxide gets is part of part of cellular respiration. It's the waste product from cellular respiration and burning things, burning fossil fuels. You find carbon in all of the fossil fuels: coal, oil, natural gas. It's in food. So when you eat stuff, one of the main components in the food that you eat is carbon. And carbon also has what we call allotropes. Okay, these are different molecular structures for the same element. So like graphite versus diamond. Diamond has a very rigid structure, graphite as well. So here's what the structure of the diamond would look like from an atomic level. Here's what it looks like from graphite, or with graphite at an atomic level. Okay. There's also what's called Buckminster fullerene. These were discovered in the 1980s. These are very, very strong molecules that can be used for all sorts of stuff. I don't know if I ever, last year, you guys might have watched a documentary about the space elevator that they're trying to develop. And in order to get the elevator to go all the way up into space, you can't use like a regular cable because it would be too heavy. It wouldn't be able to, it would fall right back down to the earth because of gravity. But Buckminster fullerene, or buckyballs, are the molecules used to make these carbon nanotubes, is very, very strong, and it's very lightweight, and they could use that they're hoping they can use that to create a cable system to take stuff out to space. It'd be pretty cool if they could do that. They could build solar panels out in space, or a massive focus of like mirror system where we can gather the sun's rays and focus it onto one solar location on Earth and create a whole bunch of electricity through compressed microwave type electromagnetic waves. Sorry. Silicon and germanium, those are also metalloids. Again, silicon is the second most abundant element on Earth's surface. We find it in sand and rocks. These are what we call semiconductors. Okay, so they'll conduct electric current if the circumstances or the conditions are right. But the thing is, they don't overheat. A lot of times, silicon gets used for things like hot pads for like grabbing stuff out of the oven, because it doesn't transmit heat, or it doesn't conduct heat very easily. So you could hold on to something that's very, very hot if you're wearing like silicone gloves, or like hot pads or trivets, things like that. Oftentimes will have silicone in them. Then there's a nitrogen group. Okay, nitrogen and phosphorus are necessary things for human DNA. All living things have to have nitrogen and phosphorus because all living things have DNA. And then finally, we're to the oxygen group here. This is the last of the mixed groups. Some of these are what we call synthetic element, or we also have synthetic elements. By 1935, all but 4 elements under 92, so uranium and below, had been discovered. All of the other ones are synthetic, meaning that they have to be created in a laboratory because the conditions on Earth are not right. Okay, so ones that are, if you look at the periodic table in the back of the room over there, and I know that's kind of pointing the opposite direction, it's actually that way now. The element symbols that are sort of hollow or they're not shaded, those are all ones that have to be made in a laboratory because the conditions on the surface of Earth just aren't right for them to be made. Okay, so that's these with this coloring, this purplish color. Okay, that's it for this chapter. I hope you guys are all doing well. You're keeping up to speed with the worksheets. If you have questions, comments, concerns, you're not getting something, please let me know. This chapter is pretty straightforward, but in the next chapter, we're going to get into more complicated stuff like chemical reactions and balancing chemical equations and stuff like that, and how to name chemical compounds. And so it's going to get more challenging. I need you guys to stick with it, and you should do just fine. Okay. Until next time, I hope you guys are doing well, and you're making good choices about who you're spending or sharing air with.